Okay, so I'm going to do one last example just using Coulomb's law, which is an example where the forces are not collinear, where they're not all on the same line. So this is example 21-3 from the textbook, which asks us to find the force on charge 3. Force on charge 3, which is this charge here, due to the forces exerted on it by charge 2 and charge 1 along the x-axis. So charge 3 is on the positive y-axis. And hopefully you can see that charge 2, which is a positive charge, and charge 3, which is a positive charge, will repel one another, so there'll be a force in the positive y direction between charge 2 and charge 3. Charge 1 is a negative charge, so it will attract this charge, but it will attract it not in the x direction or the y direction, but at some angle, actually a 30-degree angle from the x and the y direction. So in order to find the net force on charge 3, we're going to have to add together this force and this force. So we can find those two forces, call it F23 and F13 individually. Then we'll have to break this force down into components and add those two together. Before we go any further, it would be probably a good idea just to practice your vector addition, since we haven't done a problem like this in kind of a long time, to actually pause the video right now and try to work through this example on your own. And after that, I'll come back and we'll work through the solution. So if we look at the situation, we can calculate these two forces individually. We can keep track of the direction of the vectors ourselves. We don't have to worry about the signs of the charges. We can just explicitly note the direction of those vectors. So the force between charge 2 and 3 is going to be equal to Coulomb's constant, or 1 over 4 pi epsilon naught, times the product of the two charges. The charges are 65 microcoulombs and 50 microcoulombs, divided by the distance between those two squared, which is 30 centimeters, or 0.3 meters squared. So if we pull up our calculator, oops. I don't know why you can't see the calculator. Okay, so if we calculate this force, that's 50 microcoulombs, so 50 times 10 to the negative 6 times 65 microcoulombs, 65 times 10 to the negative 6 equals, divided by 0.3 squared, times this electrical constant, which is 8.99 times 10 to the 9th. That gives us 324.6. We'll round that up to 325, let's say, newtons. And that's 325 newtons in the positive y direction. Now we can do the same to find the force between 1 and 3. It's going to be the Coulomb constant times the product of the two charges. Charge 3 is still 65 microcoulombs. Charge 1 is equal to negative 86 microcoulombs. We don't need to put that negative in there because we're keeping track of the directions by hand. And the distance between them, they were nice enough to actually calculate the hypotenuse of this triangle for us, is 0.6 meters. And we can't forget to square that. So we go back to our calculator and we multiply 65 times 10 to the negative 6 times 86 times 10 to the negative 6 divided by 0.6 squared times 9 times 10 to the 9th. Oops. Oh, I missed an exponent somewhere. Let's try that again. 65, I'm not used to this weird little on-screen calculator, times 10 to the negative 6 times 86 times 10 to the negative 6 equals, divided by 0.6 squared equals, times 9 times 10 to the 9th equals 139.75. We'll go ahead and round that up to 140 newtons. So the force that 1 exerts on 3 is equal to 140 newtons at a 30-degree angle below horizontal. So in order to add these two vectors together to find the net force, we have to break that down into horizontal and vertical components. So we can write F13x and F13y as respectively. If we want and we have to decide what our 30-degree angle is. So if we're measuring 30 degrees from here, the y component is going to be 140 newtons times the sine of 30 degrees. So this is 140 newtons times the sine of 30 degrees. And oh sorry, I had them in the wrong order. The y component is going to be 140 newtons times the sine of 30 degrees. And the x component is going to be 140 newtons times the cosine of 30 degrees. So we can calculate those. Is my calculator in degrees mode? 30 degrees sine, yes. So 30 degrees is, sine of 30 is half times 140 is going to be 70. So that's 70 newtons for the y component. 70 newtons. And that's in the negative y hat direction. And 140 times the cosine of 30, 30 cosine times 140 is 121.2436, so we'll just round that to 121. Probably actually even round it to 120, that'd be fine. Oops, I lost my window for a second. 120 newtons, and that is in the positive x direction. Now we need to find the total force, which is the sum of these two forces. The x component of the total force is just equal to the x component of F13, because that's the only force acting in the horizontal direction. So that's 120 newtons. The y component of the net force is going to be equal to, if we call up the positive direction, it's going to be this force, the force that that 2 is pushing up with, minus the y component of F13. So that's going to be 325 newtons. Switch back to my pen. 325 newtons minus 70 newtons, which is 325 minus 70, 255 newtons. So that means the total force, the net force on charge 3 is going to be equal to the square root of the squares of the components the square root of 120 newtons squared plus 255 newtons squared, which is equal to 120 squared plus 255 squared equals that. Square root of that is, oh, sorry, I missed a calculator mistake. Let's try that again. 120 squared plus 255 squared equals, square root of that is 281.8, or 282 if we round that off. Newtons. And that is the answer in your book. Your book rounds that off to 290 newtons because they're just using two significant figures. One last step that we would need if we wanted to get a complete answer to this problem is to find the angle of the resultant force. We can do that, I suppose, if we want to do that. What are the components? The components are 120 in the positive x direction and 255 newtons in the positive y direction. Right? We know the force is in the positive y direction because this was smaller than that. So if we want to know the angle that this force makes with the horizontal, if it has a x component and a y component of, what were they again? 120 and 255 respectively. So 120 newtons and 255 newtons. I haven't drawn this to scale. This angle, okay, theta is going to be equal to the inverse tangent of 255 over 120. Let's see if I know how to do that on this weird little on-screen calculator. Clear. So 250 divided by 120 is going to be a little more than 2. And if I want inverse tangent of that, I get 64-ish degrees. And is that what your book gets? 65 degrees. Okay, so the angle is 65 degrees, sort of north of vertical, upwards from the x-axis, from the horizontal positive x-axis. Okay, so let me really quickly, let me get this calculator out of the way. Actually, I'll just switch back to this. So what I would recommend is working through the next few examples in the book. That would be example 21-4, and then maybe 21-6, 21-7. I'll post a link up to, well, after I post the videos, I'll post a kind of to-do list for you to do between Tuesday and Thursday. On Thursday, I'll post some more lectures about finding the electric field of more complicated configurations of charges, not just point charges, but extended objects like lines and disks and loops of charge. And then we'll do that on Thursday, and then next week we will cover Gauss's law. I'll also post a short Canvas homework assignment using Mastering Physics after I post these videos, so keep an eye out for that.